Hi there, I'm Mrs. Carter. I wanted to make a quick video for you guys about states of matter. So this is something you should have learned about before, but we want to review. So I'm going to get myself out of here so you can see everything. So you should be taking notes on this in your either in your notebook or in the Google Doc that we have given you. First thing we want to talk about are just the differences between solids, liquids, and gases. And so you did some of this in your notes. So remember, solids are going to have those particles closely packed together. They are going to be really kind of fixed in their positions, and they're not going to be moving around that much. They are still moving, but they are not moving around nearly as much. They're kind of wiggling in place. So think about you guys normally in your regular classrooms, you would be kind of wiggling back and forth in your seats, a little antsy maybe. But liquids are like when you get up and move around the room. Okay, those particles are moving a lot more. They're gonna kind of conform to the shape of the space that they have. Whereas gases are like when you get up and move out into the hallways. You really expand the space between you and peers, and you can move much more freely. Um, to think about why that is, we want to think about then the forces between the particles. We call these interparticle forces. So inter meaning between. Those interparticle forces in a solid are strong enough to keep those particles in that fixed position, as opposed to liquids where there is an attraction between the particles, but it's weak enough that those particles can still slip past each other. And in gases, we consider that there are none. They're so far apart that they don't have any attraction or repulsion for each other. When we talk about solids, the shape that they take on is considered definite, meaning it can hold its own shape without a container. So I have a solid object like my cell phone, and it will hold its own shape without it being in some sort of container. Whereas liquids like water or milk or something, they are indefinite in their shape. So they will take on the shape of whatever container they're in. Same thing with gases. Gases will take on whatever shape that container is, which is why we can take gases and put them into balloons and make crazy balloon animals. In terms of volume, we talk about volume for these different things and how much we can compress them. So solids and liquids have definite volume, meaning I cannot compress those particles closer together. Okay, so you probably know this if you've ever fallen down on the sidewalk. It's not like the sidewalk is compressing to kind of have any give, really. Same thing if you've done a belly flop in the pool. Those particles of water are not really able to compress at all easily to get you so your stomach doesn't hurt. Indefinite is what we have for gases, though. Those particles can be compressed together, and that's why we can squish a whole bunch of them into a small container like you might get for your gas grill or something like that. In terms of density, solids are going to have the highest density, whereas gases have the lowest density. Liquids are going to be somewhere in between. There's, obviously there's a range there, but gases are going to have the lowest density, and it's about 1/1000th of the density of a solid or a liquid. So they're way less dense. Little blast from the past here. We do want to think about our types of energy. So we talked about this back in iSTEM, but remember, kinetic energy is the energy of a moving object. So it's directly related to the temperature. So when we're talking about the temperature of particles, we are talking about the average kinetic energy of those particles. The potential energy is the stored energy for particles, and this is both based on the intra, meaning within, and the intermolecular bonds in a molecule. So the bonds within a molecule and the bonds from one molecule to the next both have potential energy, and that potential energy must be overcome or stored during a phase change. Okay, so we want to think a little bit more about some of those phase changes. Before we do that, I'll mention that we are going to focus mainly on the 3 states of matter that you will most commonly see. That doesn't mean that there aren't other phases of matter. Plasma is actually the most common form of matter in the universe. we just don't commonly deal with it in the lab. So plasma is a gas of charged atoms and free electrons. So basically, we've taken the atom, we've run maybe electricity through, or it's high enough heat that the electrons have been ripped off and they are separate. It's the most common state of matter, like I said, in the universe because it's what stars are made of. The Bose-Einstein condensate is another one. This is a group of atoms that are cooled to within a fraction of a degree of absolute zero, which is 0 Kelvin, meaning they are very close to getting to that point, 0 Kelvin, where there would be no particle movement at all. So the Kelvin scale measures things it gives a temperature measurement in terms of particle movement directly. And so 0 Kelvin would be zero particle movement. And we've gotten really close, but we haven't gotten exactly to it. Thinking about phase changes then, and for this part, you should be able to double click on the diagram that is in your notes. You should be able to add labels to the text boxes that are there. But if we start off and we think a little bit about these changes, the big thing is notice what's happening to the spacing of our particles as we go from solid to liquid to gas. The spacing between those particles is getting much greater as we get to the gas phase. Notice that it's not at all the size of the particles that's changing, it's just the space between them. So when I go from solid to, and we'll start here, the kind of the normal ones you're used to hearing about probably, solid to a liquid by adding heat, I would just call that melting. And so we say the temperature that occurs at is the melting point. When I am going from adding more heat from a liquid to a gas, then we call that vaporization. And that temperature that occurs at is called the boiling point. If I go directly from a solid to a gas, that would be called sublimation. And so this is the type of thing that you see if you have ever seen dry ice, which is solid carbon dioxide. It will kind of let off what looks almost steam-like, but it's not actually steam. It's super cold carbon dioxide gas that's coming off of that because it is actually going directly from a solid into a gas. If I think about cooling, so starting at a gas and coming down, I have first, when I go from a gas to a liquid, condensation. And so, when we're thinking about the weather, and we see this a lot right now, that we get these very, kind of dewy mornings where we have really wet grass, not because of rain or anything, but because of the condensation that has occurred. And so that condensation point is in weather what we call the dew point. So you'll sometimes hear them talk about that on the weather in terms of the how humid it is. They'll be describing the dew point. If we continue cooling a liquid and turn it into a solid, we call that freezing, and it's measured at the freezing point. Notice that the freezing point and the melting point here are the same. That's a big area of confusion. A lot of people think that they are not the same, but they really are. The freezing point and the melting point are exactly the same temperature. And finally, if I make one big jump from a gas all the way directly to a solid, we call that deposition. And so deposition is something that you might not have much experience with, but deposition occurs when, for example, chemists might want to put layers onto a computer chip to build that computer chip up one atomic layer at a time to build the structures that they need. So the diagram on the top here is one that we normally, that we can look at and gives us some information, but we normally as chemists actually look at this second diagram, and it's called a heating curve. And it's showing us the same thing, but it's really giving us a better idea of what is happening and the temperatures that these changes are happening at over time. And so if we look at this particular graph, you'll notice that it says energy added as heat down here at the bottom. It could also just be labeled as time, and that we're basically adding this energy over time. And then the temperature is along the y-axis. Every time we have a phase change, it ends up being a flat line without any slope. So when we see a graph like this, The spots that are flat are going to be our phase changes, and they're going to represent some of those special numbers that we can use to identify substances. Keep in mind that our boiling point and our melting point are really good physical properties of a compound that we can use to help identify it. That's it for now on phase changes.